Okay, and we've gone from discussing simple sugars, which are known as monosaccharides, to disaccharides, to now polysaccharides, where we can make very long chains of sugars. And these are really useful in biology as either structural components for cell walls or for energy storage or a number of other things. And so, for instance, we have the repeating units for three polysaccharides shown here on the right. One of them is cellulose, which is in the upper left-hand corner of the slide. Another was alpha amylose, which is in the upper right-hand corner. Another one is chitin. So we can have different, for instance, different repeating disaccharide units, which act as the monomer of a polymeric chain. So, for instance, for cellulose, the monomer, the simple sugar subunits of this disaccharide, if that's how you want to think about it, are two glucose molecules. More importantly, for cellulose, these are both the beta anomer of glucose. If you look in the figure, where the glycosidic bond is on the same side as the CH2OH, so this 6 carbon up here for glucose. So this is on the left-hand side, this is the 1 carbon forming a glycosidic bond with the 4 carbon of the second glucose. So this is a beta 1,4 linkage. Okay. For alpha amylose, as the name implies, this is actually through the alpha anomer. So these are both glucose, so the exact same compound. So these both derive from glucose, except this is now the alpha anomer. And you can see that because the glycosidic bond on the first glucose is on the bottom, so it's on the opposite side of the 6 carbon where the CH2OH is. Okay, and so again, this is the anomeric, this is what would be the anomeric carbon for glucose. So this is the alpha 1, and that is linking to the 1, 2, 3, 4 of the glucose on the right. All right. Another one that we can look at is chitin. And so chitin is a modified sugar. It's basically glucose if you look at it. So if you look at these, you can see that the functional groups behave in a similar fashion. So remember, glucose, they alternate sides on the ring each time. So starting for the 1, we start on the top. That's where the glycosidic bond is. So this is the beta anomer. And then we have a functional group on the bottom. For the 2 carbon, the 3 carbon, the functional group is on the top. The 4 carbon, the functional group is on the bottom. The 5 carbon, the functional group is on the top. And then we have our 6 carbon up here. And so this is just like, this is similar to beta glucose, the beta D-glucose, except that at the 2 carbon, we have this modification where we have this N-acetyl group to form N-acetylglucosamine. And so we can have a polymer chain of N-acetylglucosamine. And again, we can look at the linkages. So this is in the beta form once again. So here's our 1 carbon on the left-hand side, and then we form a linkage with the 1, 2, 3, 4 carbon on the other side. And so while these two are largely derived from glucose, this one is from glucosamine, or more specifically, more correctly, N-acetylglucosamine, because that functional group on the 2 carbon is an N-acetyl group. And so in this way we can form nature can form a variety of different polymers that are useful for different functions. For instance, remember that the only difference really between cellulose and alpha amylose, while we're still using glucose as the monomers, is the difference between the polymer being between the beta anomer or the alpha anomer. And so this produces complete, oh, sorry about that. Let's try that again. There it is. Okay, so this has completely different structures. So remember, glucose in the beta anomer, all of the functional groups are on the equatorial plane, right, of the chair. And so we can see in this upper right-hand corner, these are sheets of cellulose. So there are polymer chains of cellulose, and those can run in between each other, and they form hydrogen bonds in between each other, between the OH groups, which can act as both hydrogen bond donors and acceptors. And so there are these hydrogen bond linkages, or rather interactions, I should say, between strands of cellulose. And then on top of that, that makes these nice sheets. And then the sheets can then also stack on each other like this to form hydrogen bonds between these sheets, and you get basically sheets of cellulose that stack on each other. Meanwhile, alpha amylose, because this is the alpha anomer, now one of the hydroxyl groups is no longer in the equatorial plane. Instead, it's in the axial, in an axial position. And so they can't form sheets like this. So instead what happens is they form these these helical structures, secondary structures, which are shown here on the bottom hand right for alpha amylose. And that gives it a completely different property and a completely, therefore, different structure and a different function in biology.